In 1949, a quiet logician gave Albert Einstein a birthday present, and it unsettled him. Kurt Gödel had been studying Einstein's equations, the equations of relativity, and he had found something hidden inside them. A universe allowed by the mathematics, in which you could board a rocket, fly a long arc through space, and arrive back in your own past. Not a metaphor, a real path through time, looping back to where it began. Tonight, we follow that discovery, why it troubled the man who built the theory, and why our universe may quietly forbid what his equations permit. Settle in. A like and a subscribe help. Tell me, where are you watching from and what time is it there? Picture a small town in New Jersey in the year 1949, Princeton. Quiet, tree-lined, ordinary, and along its sidewalks, most days, two men walking slowly together, deep in conversation. One of them you would recognize instantly, the wild white hair, the soft, sad eyes, the most famous scientist who has ever lived, Albert Einstein. The other, you, would probably walk straight past a thin, precise, formally dressed man with round glasses and a careful, almost fragile manner. His name was Kurt Gödel, and among those who understood such things, he was considered the greatest logician since the ancient world. These two were friends, close friends in fact, in the way that two profoundly serious minds can be. Einstein, near the end of his life, is said to have remarked that his own work no longer meant much to him, and that he came to the Institute mostly for the privilege of walking home with Gödel. They would set out together and talk in German about physics, about mathematics, about philosophy, about time. They were an odd pair, the warm, rumpled, world-famous physicist and the austere, withdrawn, almost otherworldly logician. But they shared something rare. Each was, in his own field, a person who had looked deeper into the foundations of reality than almost anyone before, and found, down there, something strange. And in 1949, for Einstein's 70th birthday, Gödel decided to give his friend a gift. Not a watch, not a book. Gödel gave Einstein a universe, a new solution to Einstein's own equations, a mathematically valid description of a possible cosmos that no one had ever found before. And hidden inside that gift was something that would quietly disturb Einstein for the rest of his days. And that has never been fully laid to rest in all the decades since, because in the universe Gödel had discovered you could travel into your own past. Let that sit for a moment. We are not talking about science fiction. We are not talking about a fanciful story or a loose metaphor. We are talking about a rigorous, exact, mathematically airtight solution to the equations of general relativity, the very equations Einstein had spent a decade of his life building, the equations that describe gravity and space and time and have passed every experimental test ever thrown at them. Gödel took those equations, the crown jewel of 20th century physics, and he found a universe that obeys them perfectly. A universe fully consistent with everything Einstein had written. And in that universe, the path of an ordinary traveler could loop around through space and time and return to the very moment it started. The past was not gone. In Gödel's universe, the past was a place you could go. This is one of the strangest episodes in the history of physics, and tonight we are going to walk through it slowly, the way Einstein and Gödel walked through Princeton, taking our time, letting each idea settle before reaching for the next. We are going to understand what Gödel actually found and how it could possibly be hidden inside Einstein's equations. We are going to understand why it disturbed Einstein so deeply, even though he was the one who had opened the door. We are going to understand what Gödel, the logician, was really trying to say, because his goal was not really time, travel at all, but something far more unsettling about the nature of time itself. And finally, we are going to understand why most physicists believe that our actual universe does not permit any of this, even though the mathematics says it could. The math allows it. Reality, as far as we can tell, forbids it. And the gap between those two facts is one of the most haunting things in all of science. But to feel the weight of what Gödel did, you first have to understand who he was, because that is part of why this gift was so unsettling. Kurt Gödel was not a physicist by training. He was a logician, a mathematician of the Brahma, most abstract and rigorous kind. And before he ever touched Einstein's equations, he had already done something that ranks among the most profound intellectual achievements of all time. In the early 1930s, while still a young man, Gödel proved what are now called his incompleteness theorems. And what those theorems showed was, in a sense, a kind of limit built into mathematics itself. For centuries, mathematicians had dreamed of putting all of mathematics on a perfect, complete, self-contained foundation, a system of axioms from which every true statement could be proven, with no gaps and no contradictions. It was the great project of the age. And Gödel, almost single-handedly, proved that this dream was impossible. He showed that in any sufficiently rich mathematical system, there will always be true statements that the system itself can never prove. There will always be truths beyond the reach of the rules. Mathematics, he proved, can never be both complete and consistent. There is always something true that slips through. This is hard to overstate. Gödel had found a permanent, unremovable hole in the foundations of mathematics, the most certain and rigorous body of knowledge humans possess. He had shown that even there, in the realm of pure logic, there are limits to what can be captured, truths that exist but cannot be proven. It was a discovery that shook mathematics to its core, and that still echoes through philosophy and computer, science and logic today. And it tells you something about the kind of mind Gödel had. He was a person who looked at the most solid, trusted foundation imaginable and found the crack in it. He was drawn by his very nature to the hidden limit, the overlooked possibility, the thing the system permits that no one noticed. So when this man, this particular man, the man who had found the hole in mathematics, turned his attention in his later years to Einstein's theory of gravity, you might already feel a small shiver of anticipation, because Gödel did to general relativity exactly what he had done to mathematics. He looked at the trusted structure, the equations everyone thought they understood, and he found the thing hidden inside that nobody had noticed. Only this time, the hidden thing was not an abstract limit on proof. It was a universe in which time bends back on itself, in which the future can lead to the past, in which the most basic assumption we make about reality, that what is done, that the past is fixed and gone, quietly fails. It is worth pausing on how unlikely this collaboration was, because there is real poignancy in it. Here was Einstein, who had revolutionized our understanding of space and time, who had taught the world that time is not absolute, that it bends and stretches and slows. And here was Gödel, who had revolutionized our understanding of logic and proof. The two of them, walking together in a small American town, two refugees from a settler, Europe that had torn itself apart, two of the deepest minds of their century, talking quietly about the structure of reality. And out of those conversations, out of that friendship, came this gift, this strange and beautiful and troubling thing, a universe that lets you visit your own yesterday, handed by the logician to the physicist on the occasion of his 70th birthday. Let me set the scene a little more fully, because the place and the moment matter. Both Einstein and Gödel had ended up at the Institute for Advanced Study in Princeton, a haven created precisely for thinkers of their kind, a place with no students to teach and no duties to perform, only the freedom to think. Both had fled Europe as it descended into horror. Einstein, the most famous refugee in the world; Gödel, a more fragile and private exile, a man whose mind was extraordinary but whose grip on ordinary life was tenuous. At the Institute they found each other. By most accounts they were an unlikely friendship that became a deep one. The older man, warm and humorous and weary; the younger man, precise and anxious and brilliant, and yet between them an understanding that neither seemed to find with many others. They walked, they talked, and in those walks, two of the most penetrating minds of the century turned the foundations of reality over and over between them. Gödel was, by any account, a strange and singular person. His logic was flawless, and his caution was total. He trusted reasoning above all else, and he applied it everywhere, sometimes to unsettling effect. There is a famous story which captures him well, that when he studied for his American citizenship test, he became convinced he had discovered a logical flaw in the United States Constitution, a loophole through which the country could legally become a tyranny, and that he was barely talked out of explaining this to the judge at his hearing. Whether every detail of that story is exact, it rings true to the man. He was someone who could not stop himself from finding the hidden flaw, the unnoticed possibility. The door no one realized was unlocked. He did not seek out paradoxes to be provocative. He found them because he looked harder and more honestly than other people. And reality, when you look at it that hard, turns out to be full of doors no one meant to leave open. This is the temperament that you must keep in mind, because it is the key to understanding what he did to Einstein's theory, Most physicists who worked with general relativity used it as a tool. They wanted to describe the real universe, the one we live in. And so they looked for the solutions that matched what they saw in the sky, the expanding cosmos, the orbits of planets, the bending of starlight. They were not especially interested in strange solutions that seemed to have nothing to do with reality. But Gödel was a logician. To him, the question was not only what universe we happen to live in. The question was what the equations permit. What is logically possible within this theory? And that is a profoundly different question. And it is the question that led him straight to the hidden door. Think of it this way. Einstein's equations are like the rules of a game. Most players use the rules to play ordinary games, the kinds of games that come up naturally. But a logician does not just play the game. A logician asks what every possible move the rules allow would lead to, including the moves no one would ever think to make. And Gödel, asking that question of general relativity, found a legal move, a perfectly valid configuration of matter and space-time that produced a universe nobody had imagined, a universe that obeyed every rule Einstein had written and yet behaved in a way that violated the deepest intuition we have about time. The move was legal. That was the whole point. It was not a mistake, not an approximation, not a fudge. It was a clean, exact, rigorous solution. The rules of Einstein's own theory permitted a world in which you could return to your own past, and no one had noticed until a logician came looking. And here is what makes it bite. The thing I want you to carry forward into everything that follows. We hold, all of us, a belief about time so deep that we rarely even notice we hold it. The belief is that the past is gone, that what has happened and is now closed, sealed, beyond reach, existing only in memory and consequence. The present is real, we feel, and it slides forward, and behind it, the past falls away into non-existence. This feeling is so total that it seems less like a belief and more like a simple fact of reality, as basic as the ground beneath your feet. And what Gödel found, hidden in Einstein's equations, was a universe in which that feeling is wrong, a universe in which the past has not fallen away at all, in which it is still there, still a place, a region of space-time you could, in principle, steer a ship toward and reach, not a recording of the past itself as real as the present, because in such a universe the very distinction between past and present that we take for granted does not hold in the way we think it does. That is what was wrapped inside the birthday gift, not a clever trick, a quiet, rigorous demonstration that one of our most fundamental assumptions about reality, the goneness of the past, is not guaranteed by physics. It is, at best, a feature of the particular universe we happen to inhabit, and not a law that holds in every universe the equations allow. And if it is only a local accident rather than a deep necessity, then we have to ask what time really is, and whether its flow, its passing, its relentless forward motion is a true feature of the world or a kind of illusion. That question is the dark heart of the whole story, and Gödel aimed it deliberately and precisely at the man who had done more than anyone to teach the world that time is stranger than it seems. We do not know exactly what Einstein felt when he first saw it, but we know he took it seriously, because he was not a man to dismiss rigor, and Gödel's work was nothing if not rigorous. And we know it troubled him because in his published response he admitted as much in his careful way, and raised the question of whether such universes might somehow be ruled out by physical considerations, even if the mathematics allowed them. That question, whether reality forbids what the equations permit, is the question we will follow all the way to the end of this journey. It is still, in some sense, open. There is a deep irony here worth sitting with before we go on. Einstein was the one who had first loosened time from its moorings. Before him, time was thought to be absolute, the same everywhere, a universal clock ticking identically for everyone, a fixed and even background against which all events played out. It was Einstein who shattered that picture. He showed that time runs differently for observers moving differently, that a clock on a fast-moving ship ticks slower than one at rest, that time near a heavy mass runs slower than time far away, that there is no single universal now shared by all observers. He took the rigid, absolute time of the old physics and made it flexible, personal, woven together with space into a single fabric. He had already made time far stranger than anyone had dreamed, and so, in a sense, Einstein had opened the door himself. He had taught the world that time could bend. Gödel simply walked through that door further than Einstein had intended, and found at the far end of it a place where time bends so completely that it closes into a loop. That is why the gift was so unsettling and so fitting and so precisely aimed. It did not come from outside Einstein's theory as an objection or an alternative. It came from inside it as a consequence. It was Einstein's own creation, followed to one of its logical conclusions by a mind relentless enough to follow it all the way. You cannot dismiss a thing like that. You cannot say it violates the theory, because it is the theory. You can only ask, as Einstein did ask, whether nature has some additional reason beyond the equations to forbid what the equations allow. And that question pulls you out of physics and into something deeper, into the relationship between mathematics and reality, between what is possible in principle and what is actual in fact. I want to be honest with you that we will not fully resolve that question tonight, because no one has fully resolved it. What we will do is understand it as clearly and as deeply as we can. We will see exactly what Gödel built and how it works. We will feel why it disturbed Einstein. We will follow Gödel into the strange philosophical conclusion he drew from it, his real target all along, which was nothing less than the claim that the passage of time is an illusion, and we will come to understand why our own universe, as best we can tell, does not contain these loops, and what that gap between the possible and the actual might mean. By the end, you will not have a tidy answer. You will have something better, a genuine understanding of one of the deepest open questions about the nature of time, seen through the lens of a friendship between two extraordinary men and a birthday gift that was really a riddle. So this is where we begin. Two friends in Princeton, a birthday, a gift that was also a kind of riddle, a universe pulled from Einstein's own equations, in which the past is not gone but waiting, reachable, real. To understand how such a thing is even possible, we have to go back to the equations themselves and understand what Einstein had really discovered about space and time. Because the strangeness was there from the beginning, hidden in the foundations, waiting for a logician patient enough and strange enough to find it. Let us go there now, gently, into the fabric of space-time itself. To understand how a universe can loop time back on itself, we have to understand what Einstein actually discovered about space and time. So let us build it carefully from the ground up, because the strangeness of Gödel's result lives entirely in the details of this structure. Begin with the old picture, the one we all carry instinctively. Space is a kind of empty stage, a fixed three-dimensional container in which things sit and move, and time is a separate thing, a universal clock ticking away in the background, the same for everyone, everywhere, carrying the whole universe forward together from past to future. Space here, time there, two separate absolutes. This is the picture in your bones. It is also Einstein showed wrong. Einstein's first great revolution, special relativity, broke the separateness. He showed that space and time are not two independent things, but two aspects of a single, unified entity, which we now call space-time. They are woven together. How much time passes between two events, and how much space lies between them, are not separate fixed facts. They depend on how you are moving, and they trade off against each other in a precise way. Move very fast, and your time slows relative to someone at rest, while distances along your motion contract. Time and space bleed into one another. They are not two stages, but one, a four-dimensional fabric in which every event has a location in both space and time at once, a single seamless whole. Then came the second, deeper revolution, general relativity, and this is the one we need. Einstein asked what gravity is, really. The old answer from Newton was that gravity is a force, an invisible pull reaching across space between any two masses. Einstein replaced that entirely. He proposed that gravity is not a force at all. Gravity is the bending of space-time itself. A massive object, like the sun, warps the fabric of space-time around it, curving it, the way a heavy ball resting on a stretched sheet creates a dip around itself. And other objects moving through that curved region simply follow the straightest available path through the curvature. The Earth does not orbit the curvature. Sun, because a force reaches out and pulls it. The Earth orbits because the Sun has curved the space-time around it, and the Earth is rolling along the straightest path it can through that curved geometry. What we feel as gravity is the shape of space-time, guiding our motion. This is the central idea. and it is worth letting it land fully, because everything follows from it. Matter and energy tell spacetime how to curve. The curvature of spacetime tells matter how to move. The two are locked together in a precise mathematical relationship. And that relationship is what Einstein's field equations express. On one side of the equations sits the matter and energy in a region. On the other side sits the curvature of space-time there. The equations say how much the one bends the other. Solve them for a given arrangement of matter, and you get the shape of the space-time that matter produces. That shape is everything. It tells you how clocks run, how objects fall, how light travels, what paths are possible. The geometry of space-time is the stage and the script at once. Now I need to give you two more tools, because they are exactly the tools Gödel used, and without them his result is invisible. The first is the idea of a world line. Think of any object, yourself, a planet, a particle of light. As it moves through space over time, it traces a path, not just through space, but through space-time, through all four dimensions at once. That path is its world line. Your world line is the complete record of where you are at every moment, drawn as a single, continuous curve through the four-dimensional fabric. Right now, sitting still, you are still moving through space-time, because you are moving through time, advancing into the future second by second. Your world line climbs steadily through the time direction. Everything that exists traces such a line, a thread through space-time marking its whole history from beginning to end. In this picture, the history of the universe is not a movie, playing frame by frame. It is a vast, fixed, four-dimensional tapestry woven through with the world lines of everything that ever was or will be. The second tool is the light cone, and this is the one that enforces the order of cause and effect, the very thing Gödel's universe will violate. Here is the idea. From any event, any single point in space-time, light can spread outward in all directions. Because light travels at a fixed maximum speed, the set of all places that light from that event can reach, traced through time, forms a cone shape in space-time, opening into the future. Anything that happens at that event can only influence things inside that future cone, because nothing can travel faster than light to reach beyond it. Similarly, only things inside the past cone, the mirror image opening backward, could have influenced the event. The light cone divides space-time from the viewpoint of every event into three regions: the future, which this event can affect, the past, which could have affected it, and the elsewhere, too far away in space to be reached at light speed, which is causally disconnected. This light cone structure is the backbone of causality in relativity. Your world line and the world line of anything slower than light must always stay inside its own future light cone as it moves forward. You can only ever move into your own future, never sideways into the unreachable elsewhere, and never ever backward into your own past. The light cones are like a set of one-way signs woven into the fabric of space-time at every point, all pointing the same way, toward the future. Follow them and you go forward in time. They make the past unreachable. They are the reason cause comes before effect. They are the reason in ordinary space-time that you cannot visit yesterday. And here is the crucial fact, the hinge on which the entire story turns. In flat, empty space-time, all the light cones point the same way, neatly lined up, future pointing, uniformly forward, and causality is safe. But space-time is not always flat. Mass and energy curve it. And when space-time curves, the light cones tilt. Near a heavy mass, the cones lean inward toward it. The curvature of space-time literally tips the local definition of future and past. In most situations, this tilting is mild and causes no trouble. But the equations do not forbid the cones from tilting a great deal. And if you could find an arrangement of matter that tilted the light cones far enough, around a large enough region, then following the future direction of the cones, always moving forward by every local measure, you might find the cones leaning so far over that the path they trace curves around and reconnects with its own past. You would have moved forward into the future the entire way, and yet arrived behind yourself in time. That is the door, and Gödel found the arrangement of matter that opens it. Let me slow down and make these ideas more solid, because they are doing all the heavy lifting, and it is worth feeling them rather than just hearing them. Take the bending of time near mass first, because it is real and measured, not a theoretical flourish. Time genuinely runs slower, deeper in a gravitational field. A clock at sea level ticks very slightly slower than an identical clock on a mountaintop, because it sits deeper in the Earth's curvature of space-time. This is not a quirk of the clocks, it is time itself running at different rates in different places, and we rely on this every single day. The satellites that run the positioning system in your phone carry precise clocks, and those clocks run measurably faster than clocks on the ground, because the satellites are higher up where space-time is less curved. If engineers did not correct for this difference, the navigation system would drift wrong within hours and become useless. So the bending of time by gravity is not a fragile abstraction, it is engineering. It is in your pocket. Space-time really does curve, and that curvature really does change how time flows, and we have built our infrastructure on top of that fact. Once you accept that gravity bends time even a little, the door is open to asking how much it could bend time if you pushed it hard enough. Now hold the picture of the world line again, and let me make it vivid, because Gödel thought in exactly these terms. Imagine drawing a diagram with space running left to right and time running upward. An object sitting still traces a straight vertical line, going nowhere in space, but climbing steadily upward through time. An object moving at a steady speed traces a slanted line, drifting sideways through space as it climbs through time. Anything that happens traces some curve on this diagram, and the whole of History becomes a still picture, a fixed pattern of lines, every event already located, every world line already drawn from end to end. This is sometimes called the block, universe view, and it follows naturally from relativity. In it, the past and the future are not different in kind from the present. They are just other regions of the diagram, other parts of the fabric, all equally real, all already there. The sense that only the present moment exists and that it moves does not obviously appear anywhere in the picture. Hold on to that, because it is exactly the thread Gödel will pull on at the very end when he turns this whole story toward the claim that the flow of time is an illusion. And now the light cones, drawn on that same diagram. At every point, draw a cone opening upward into the future and a mirror cone opening downward into the past, set by how far light can travel. A world line is only allowed to climb upward, staying within its own upward cone at each point, because nothing can outrun light. So in flat space-time, with all the cones pointing straight up and neatly aligned, every world line marches steadily upward into the future, and there is no way to curve one back down to an earlier time without tipping it outside its cone, which is forbidden. The cones are the guardrails of causality. They are why effect follows cause, why you remember the past and not the future, why the arrow of time has a direction at all on this diagram. They are, quite literally, the geometry of before and after. But remember the key fact, and now feel its full force. The cones are not bolted in place, pointing up. They tilt wherever space-time curves. Mass and energy and motion can tip. Picture a row of these cones, and now imagine something tipping each one a little further over than the last, so that as you move along the row, the cones lean and lean, their future openings rotating around. If the leaning continues far enough, the future opening of a distant cone could point back toward the starting region, and a world line that faithfully climbs into the future cone at every single step, never once doing anything. Locally forbidden could ride that leaning row of cones all the way around and arrive back where it started, earlier in time than it left. At no point did it move backward. At no point did it break the local rule. It went forward into the future the entire way, and the forward direction itself was bent into a circle. That is the whole secret, stated plainly. To loop time, you do not need to move backward. You need a space-time in which moving relentlessly forward can bring you home to your own past, because the local future has been tilted all the way around into a ring. The only question left is whether any real arrangement of matter, obeying Einstein's equations, actually tilts the cones that far around a closed loop. For decades, the unspoken assumption was that nothing did, that while the cones might tip a little near stars and black holes, they never tipped so far and so coherently as to close a loop. Causality, everyone quietly assumed, was safe. Gödel did not assume it. He asked the equations directly, and the equations gave him a matter arrangement that tilts the cones exactly that far. We are about to see what that arrangement is. There is one more idea to make clear before we meet it, and it is the deepest point of this whole section, the one that turns Gödel's result from a curiosity into something genuinely disquieting. It has to do with the difference between what the equations allow and what nature actually builds. We have been speaking of solutions of valid configurations of matter and space-time, but a solution to Einstein's equations is not a story or a suggestion. It is a complete, self-consistent, fully detailed universe, every bit as mathematically real and valid as the one describing our own cosmos. When Gödel found his rotating universe, he did not find a loophole or an approximation or a thought experiment. He found another whole world sitting in the same family of worlds as ours, obeying the same laws, just as legitimate, just as allowed. And in that world, the loops were real. Einstein's field equations do not describe one universe. They describe a whole infinite family of possible universes. Each valid solution to the equations is a complete, self-consistent space-time, a way a universe could be. There is a solution that describes empty space. There is a solution that describes the space-time around a single star, and another for a black hole, and another for our own expanding cosmos full of galaxies. Each one is a different shape of the four-dimensional fabric, a different valid answer to the same equations. So when Gödel found his rotating universe, he was not breaking Einstein's theory or proposing a rival to it. He was pointing at one more member of the family, one more valid solution, a universe the equations had always permitted, sitting there in the mathematics, waiting. The equations allow it. Whether nature builds, it is a separate question, and that distinction between what the equations allow and what nature builds is the thread we will follow all the way to the end. This is why you cannot wave the result away. If Gödel had merely told a story about time travel, a physicist could shrug and say that stories are not physics. But Gödel did not tell a story. He handed Einstein a geometry, a precise mathematical object satisfying the field, equations exactly. And inside that geometry, the loops were as solid and as real as the orbit of a planet. To deny the loops, you would have to deny the solution, and you cannot deny the solution because it obeys the equations. All you can do is argue that nature does not happen to build this particular allowed world. And that, as we will see, is exactly the move physicists eventually made, and exactly the move whose deeper meaning is so unsettling. It helps to see that this is exactly how relativity had always worked, that Gödel was doing something normal in method, even if his result was extraordinary. Within months of Einstein publishing the field equations, a physicist named Schwarzschild, working out the geometry around a single spherical mass, found the solution that describes the space-time around a star, and that same solution, pushed to its extreme, turned out to describe a black hole, an object so curved that not even light escapes. Nobody at first. believed black holes were real. The solution was just a piece of mathematics, a member of the family. And only decades later did we find that nature actually builds such things. Around the same time, other physicists found solutions describing an entire universe full of matter, and those solutions did something startling. They would not sit still. They described a universe that must either expand or contract, never stay static. That mathematical result, a whole class of solutions describing a changing cosmos, predicted the expansion of the universe before we had observed it. The equations spoke first. Reality, when we finally looked, agreed. So the pattern was established long before Gödel. You solve Einstein's equations for some arrangement of matter, and you get a possible universe, a complete geometry. Sometimes that possible universe turns out to match the one we live in. Sometimes it describes something we later discover is real, like black holes, and sometimes it describes something that seems to have no counterpart in reality at all, a mathematical possibility that nature, for whatever reason, does not appear to build every one of these, is a legitimate solution. The equations themselves do not tell you which solutions nature chooses. They only tell you which universes are allowed. Choosing among them, deciding which one is real, requires going outside the equations, to observation, to additional principles, to the actual sky. And this is the crack that Gödel's universe lives in. It is a perfectly legal solution. The question of whether it is ever built is not answered by the mathematics. And that unanswered question is precisely what makes it so haunting. With all of that in hand, the curving fabric, the world lines, the tilting light cones, the family of allowed universes, we are finally ready to meet the specific one Gödel found. It is built from the simplest imaginable ingredients, and yet it tilts the cones all the way around. Now let us look at the strange universe Gödel pulled out of the family, the one that spins. So what is the arrangement of matter that Gödel found? The configuration that tilts the light cones all the way around. The answer is strange and beautiful in its simplicity. Gödel found a universe that rotates, a whole cosmos spinning. Now, the moment you hear that, your mind reaches for a familiar picture. You imagine a great wheel turning, or a spiral spinning around a hub, matter whirling around some central axis like water circling a drain. Set that picture aside gently, because it is not quite right and it will mislead you. Gödel's universe does not rotate around a center the way a wheel does. There is no special central point, no hub, no axis sitting at one particular place that everything else swings around. Gödel's universe is what physicists call homogeneous, which means it looks essentially the same everywhere. Every point is like every other point. There is no center and no edge, and yet the whole thing rotates. How can something rotate with no center to rotate around? That is the first strange and wonderful idea we have to absorb. The rotation in Gödel's universe is not a spinning around a place. It is a property woven into space-time itself, present at every point, the same everywhere. To understand it, we need a subtle idea from relativity, the idea of a local standard of non-rotation. In our universe, there is a meaningful sense in which you can tell whether you are rotating, even without looking at anything outside. If you spin, you feel it. You feel the outward tug, the way a spinning carousel pushes you toward its edge, the way your arms want to fly outward if you twirl. A spinning astronaut feels it too, far from any star. There is, built into space-time, a local standard of what it means to not be rotating, and physics provides it through the behavior of freely moving objects and spinning gyroscopes. A gyroscope, left alone, holds its axis steady against this local standard. It points faithfully in a fixed direction, defining what non-rotation means right where it is. Now here is the heart of Gödel's universe. In it, the matter of the cosmos, the great dust of galaxies, rotates relative to this local standard everywhere by the same amount. At every point in Gödel's universe, if you took a gyroscope and let it settle, defining the local, non-rotating direction, you would find the surrounding matter slowly turning with respect to it. The whole material content of the universe swirls gently against the local compass of space-time at every point alike. It is not that the universe spins around a center. It is that everywhere, locally, the matter turns relative to the very fabric that defines turning. The rotation is a feature of the relationship between the matter and the space-time, present uniformly throughout, with no center, because it needs none. The swirl is in the weave. Let me give you the ingredients of the model, because they are humble, and that is part of what makes the result so disquieting. Gödel did not need exotic matter or strange energy. He filled his universe with dust. That is the actual technical term physicists use, dust, meaning a smooth, uniform distribution of matter, like a fine, even fog of particles, or galaxies spread evenly through space, drifting along without pressure, without collisions, just a gentle, uniform filling of the cosmos with stuff, ordinary matter, evenly spread. And to balance the equations and make the geometry work, he included a particular value of the cosmological constant, the term Einstein himself had once introduced into his equations, a kind of uniform background tension woven into space-time. That is all, uniform dust and a cosmological constant tuned together. From those plain ingredients, the equations produce a space-time that rotates everywhere, and in which the light cones tilt around, and in which time can loop. Sit with how unsettling that simplicity is. You might have hoped that to break causality, to allow travel into the past, you would need something monstrous, some violent singularity, some impossible concentration of energy, something so extreme that you could comfortably believe nature would never produce it. But that is not what Gödel found. He found that a smooth, calm, evenly filled universe made of ordinary dust, gently rotating, with a particular background tension, allows time loops. There is nothing violent about it. There is no catastrophe at its heart. It is, in its own way, a peaceful and orderly cosmos, and it lets you visit your past. The door to the past in Gödel's discovery is not guarded by fire. It is opened by something as mild as a slow, uniform swirl. There is a quiet irony worth noting in that cosmological constant Gödel used, because it ties the gift even more tightly to Einstein. Einstein had originally introduced the cosmological constant into his equations years earlier, for a reason that turned out to be mistaken. In an attempt to keep the universe static and unchanging, when the universe was discovered to be expanding, he reportedly regretted ever adding the term. And yet, here was that same term, the one Einstein had second-guessed, appearing in Gödel's construction as one of the ingredients that makes the time loops possible. The very piece of the equations Einstein had been most uncertain about became part of the mechanism by which his friend showed him that time could close into a circle. The gift was woven through and through, out of Einstein's own choices and doubts. Now let us see how that swirl tilts the light cones, because this is where the rotation connects to the loops. Remember that light cones tilt wherever space-time has the right kind of structure. In Gödel's rotating universe, the swirl drags the light cones along with it. Near any point, the cones point more or less upward into the future, as you would expect. But as you move outward from any point, following the rotation, the dragging effect accumulates, and the light cones progressively tilt over in the direction of the swirl. The further out you go around a loop, the more the cones have leaned, and Gödel calculated exactly that beyond a certain distance, the cones tilt so far over that their future openings have rotated enough to tip below the horizontal, so to speak, enough that the forward direction of time, the direction a traveler must always move, now leans around the loop and begins to point back toward the past. This is the crucial result, and it is worth stating very carefully so its strangeness is exact. There is no place in Gödel's universe where time runs backward. Nowhere does a clock tick in reverse. Everywhere, locally, time behaves perfectly normally, flowing forward, cause before effect, light cones opening into a sensible future. If you lived at any single point in Gödel's universe, you would notice nothing wrong. Your clock would tick forward. Your coffee would cool, never spontaneously reheat. Everything local would seem entirely ordinary. The strangeness is not local, it is global. It only appears when you trace a large enough path through the whole tilted structure, step by step. The cones tilt, each one only slightly off from its neighbor, each transition perfectly normal until, going all the way around a wide enough loop, the accumulated tilt has turned the future into a circle that closes on its own past. The violation of causality is not anywhere in particular. It is in the global shape, the way all the perfectly ordinary local pieces fit together into a structure that, taken as a whole, lets the future curl back to the beginning. It helps to have an everyday image for how local normality can hide a global twist, because this is the single most counterintuitive feature of the whole construction. Think of one of those impossible staircases drawn by certain artists, the kind where you climb step after step, each step clearly going up, and after 4 flights you find yourself back where you started, having only ever ascended. At no single step did anything strange happen. Every step was an ordinary step upward. The impossibility lives not in any one step, but in how the staircase is connected as a whole. Or think of a simple loop of paper, given a half twist before its ends are joined, the shape with only one side. Walk along it, and the surface is perfectly ordinary everywhere you stand, flat and two-sided as far as you can see. And yet, going all the way around, you arrive back at your start, having somehow ended up on what was the other side. The strangeness is global, not local. Each small patch is unremarkable. The whole is impossible by ordinary reckoning. Gödel's universe is like that, but with time playing the role that up or sidedness plays in those examples. Each light cone is an ordinary cone pointing into a sensible future. Each step along a world line is an ordinary step forward in time. Nowhere do you find a place where things are locally wrong, and yet the cones are connected across the whole rotating cosmos with a kind of twist, so that following the perfectly ordinary forward direction all the way around brings you back to your own past. The loop in time is the global twist in how all the flawless local pieces are joined. This is why it took a Gödel to find it. A physicist checking the local physics at any point would find everything in order and conclude, reasonably, that all was well. Only someone who insisted on tracing the global structure, on asking where the locally ordinary cones lead when you follow them all the way around, would discover the twist. Gödel was exactly that kind of thinker, the kind who never trusts that local good behavior guarantees global good behavior, because he had already proven in mathematics that it does not. There is a beautiful subtlety here that Gödel understood deeply, and it is the same kind of insight that ran through his work in logic. A structure can be perfectly consistent and ordinary at every local point, and yet globally do something that seems impossible. Each light cone is fine. Each step forward in time is fine. The local rules are never broken. And yet the whole, assembled from those flawless local pieces, contains a path that returns to its own past. The impossibility does not live in any single piece. It lives in how the pieces connect across the whole. This is a profoundly Gödelian idea, that you can follow every rule at every step and still arrive somewhere. The rules seem to forbid, because the forbidding was never actually in the rules, only in our assumption about where the rules would lead. He had found this in mathematics, the true statement that no local application of the rules could prove. Now he had found its echo in spacetime, the past reachable by a path that never once moved backward. Let me give you a way to feel why a rotating spacetime can drag the light cones at all, because it is grounded in real, measured physics, not just in Gödel's abstract model, in general relativity. A rotating mass does not only curve the spacetime around it the way any mass does, it also drags spacetime into a kind of swirl, twisting the very fabric in the direction of its spin. This effect is called frame dragging, and it is real. A spinning, massive body, like the Earth, very slightly drags the space-time around it into rotation, so that the local standard of non-rotation itself gets twisted along with the spin. This is a tiny effect for the Earth, far too small to feel, but it has actually been measured by delicate experiments with gyroscopes in orbit, which detected their axes being gently dragged by the Earth's rotation, exactly as the theory predicted. So the idea that rotation twists space-time, that a spin can drag the local frame around with it, is not speculation. It is observed fact. Gödel's universe simply takes that real effect and makes it global and uniform, a swirl woven into the whole cosmos rather than concentrated around one spinning body. The same dragging that the Earth does faintly to the space around it, Gödel's rotating matter does everywhere, all at once, and the accumulated dragging around a large loop is what tilts the cones all the way over. There is a deep idea hiding in this that fascinated Gödel, and it connects to one of the oldest questions in physics. When something rotates, what is it rotating relative to? You feel the tug of your own spinning. But relative to what is that spin defined? One old and beautiful idea associated with the physicist and philosopher Mach suggested that rotation is defined relative to the distant matter of the universe, the great mass of all the stars and galaxies, and that the local sense of non-rotation is somehow set by that distant cosmic matter. If that were strictly true, then the matter of the universe could never as a whole be said to rotate, because there would be nothing left for it to rotate against. Gödel's universe is, in part, a direct challenge to that idea. In his cosmos, entire mass of the universe does rotate relative to the local compass of space-time, defined by gyroscopes. The matter turns against the very fabric that is supposed to define turning. This was, for Gödel, not just a curiosity, but a pointed demonstration. It showed that relativity does not force rotation to be merely relative to the cosmic matter. The local structure of space-time has its own standard of non-rotation, independent of the distant stars, and the matter can spin against it. The swirl is real and absolute in that sense, even with no center to host it. Now I should be honest about the scale of the loops, because it matters for understanding both the wonder and the limits. The closed paths in Gödel's universe are not small, and following one is not a casual undertaking. To go around a loop that returns you to your own past, you would have to travel an enormous distance across a vast swath of the rotating cosmos, and you would have to move at a sizable fraction of the speed of light for the journey. In practical terms, no rocket we could imagine building could actually make the trip, because the distances and speeds required are staggering. So even in a Gödel universe, this is not a matter of stepping into a machine and popping back to yesterday afternoon. It is a colossal voyage through space, on a scale that dwarfs anything technology could achieve. But, and this is the entire point, the journey is not forbidden by the laws of physics. It is not impossible in principle only. impossible in practice. There is a difference between something that the laws rule out, absolutely, and something that the laws permit, but that would require resources beyond reach. The grandfather paradox does not care whether the trip is convenient. It only cares whether the trip is allowed. And in Gödel's universe, it is allowed. The path exists. The geometry contains it. Whether or not any being could ever traverse it, the past sits there, connected to the present by a legal road through space-time. The mere existence of that road is what shakes the foundations, regardless of whether anyone could drive it. And let us hold, one more time, the strangeness of a universe with no center that, nonetheless, rotates, because it is genuinely hard for the mind to grasp and worth effort. Picture yourself anywhere in Gödel's cosmos. Look around. The dust of galaxies stretches off in every direction, evenly, the same in all directions, with no special point, no hub, no axis you could point to and say, there, that is what we are all going around. And yet, take out your gyroscope, let it settle, and watch. The whole sky of matter turns slowly against it. You are at a center, in a sense, because every point is equally to center. The rotation is happening around you and around your neighbor and around every point at once, because it is not a rotation around any place at all. It is a rotation of the relationship between matter and the local fabric, identical everywhere. This is one of those ideas that does not fit into the wheel and hub picture the mind keeps reaching for, and the discomfort you feel trying to hold it is the right discomfort. It is the discomfort of a real idea that our ordinary intuitions were never built to contain. Gödel lived comfortably in that discomfort. It was his native country. We have now built the rotating universe and felt how its gentle swirl tilts the cones around until the future closes into a ring. But we have not yet walked the loop itself. We have not yet stepped onto the path and followed it around and felt what it would actually mean to ride the tilted cones back to your own beginning. That is the next part of our journey. The closed timelike curve itself, the loop in time, and the dizzying questions it raises about what it could possibly mean to arrive in your own past. Let us walk it now, slowly, all the way around. Now we walk the loop. Let us step onto the path Gödel found and follow it all the way around and feel what it actually means, because this is the strangest and most vertiginous part of the whole story, and it deserves to be felt slowly. The technical name for the path is a closed time-like curve. Let us take that phrase apart, because each word is doing exact and important work. Time-like means it is a path that an ordinary object could actually travel, a path that always moves at less than the speed of light, always advancing locally into the future, the kind of path that a person, a ship, a clock could follow. It is not a beam of light and not some abstract line. It is a possible journey for a real traveler. Closed means it loops. It comes back. It returns to its exact starting point, not just in space, but in space-time, the same place and the same time, the very event it began at. Put those together and you have the full strangeness. A closed time-like curve is a journey that always moves forward in time by every local measure and yet arrives back at its own beginning. You set out into your future. You never once turn back, and your future delivers you to your past. Gödel described the journey himself in plain terms. He pointed out that in his universe, by making a wide enough trip in a rocket ship, traveling out along a sufficiently large arc, a traveler could reach into any region of the past, present, or future, and return just as. In an ordinary universe, one can travel to any distant region of space and come back. Let that comparison sink in, because it is the key to feeling what he meant. In our universe, space is open to us. We can, in principle, travel to any place and come back. Time is not open to us in that way. We are carried through it helplessly in one direction, unable to return to where we have been. But in Gödel's universe, that asymmetry is broken. Time becomes, in a sense, like space. Just as you can take a long enough journey through space and return to a place you have left, you can take a long enough journey through Gödel's spacetime and return to a time you have left. The past becomes a destination, reachable by travel, exactly as a distant city is reachable by travel. So picture the voyage. You climb into the ship at some moment, call it your departure. You fire the engines and begin a vast curving journey through the rotating cosmos, riding along with the swirl, moving always forward through your own time, your own clock ticking steadily ahead, your own experience entirely ordinary. Years pass for you. On the ship, perhaps, you age. You move into your future the whole way, never reversing, never doing anything that feels strange. And then, following the great tilted loop of the cones around through the rotating space-time, your forward path curves back and you arrive. And the moment you arrive at is your own departure. You return to the very event you left from. You could, in principle, look out the window and see yourself, younger, climbing into the ship to begin the journey you have just completed. You have traveled into your own past by traveling into your own future. The two have been joined into a circle. It is worth dwelling on how ordinary the whole trip would feel from the inside, because that ordinariness is the deepest part of the strangeness. Nothing about the journey violates your moment-to-moment experience of time. Your watch never runs backward. You never feel yourself growing younger. You never pass through some shimmering barrier-marked entrance to the past. From the traveler's point of view, it is simply a very long voyage through space, forward through one ordinary minute after another, the engines humming, the years accumulating, the body aging in the usual direction. There is no moment at which the past arrives. There is only the steady, forward unspooling of an ordinary life, which happens because of the global shape of the space-time to deliver you to a point you have already lived through. The horror, if there is horror, is not in any instant of the trip. It is only in the bookkeeping, in the realization when you Compare your arrival to your departure, that they are the same event. Locally, all is calm. Globally, the calm forward motion has carried you home to your own beginning. This is also why the closed time-like curve is so much more troubling than the simpler time dilation effects everyone has heard of. Traveling into the future is easy and uncontroversial. Move fast or sit near a strong gravitational field and your clock runs slow relative to others, and you arrive in their future having aged less. Astronauts do this very slightly every time they orbit. That kind of time travel breaks nothing, because it only carries you forward, faster than others perhaps, but still forward, the past still, sealed behind everyone. The closed time-like curve is a different animal entirely. It does not merely let you skip ahead, it lets the forward direction itself bend around and reconnect with the past, so that going forward becomes going back. That is what no ordinary effect does, and that is what Gödel found lurking in the equations, and that is what makes it a genuine assault on the structure of time rather than a mere stretching of it. This is where the mind rebels, and rightly so, because it immediately reaches for the paradox. If you can return to your own past, then you can interfere with it. The classic version is brutal and simple. Suppose you travel back and prevent your own departure. Suppose you reach your younger self about to climb into the ship and you stop them. You talk them out of it. You block the voyage. Then you never made the trip. But if you never made the trip, you never went back to stop yourself. So you did make the trip. So you did go back and stop yourself. So you did not. The logic spins in place, contradicting itself, a loop that cannot settle. This is the grandfather paradox, named for the starker version in which a traveller goes back and prevents their own grandparents from meeting, erasing their own existence, and thereby erasing the trip that did the friend. Erasing. It seems to show that time travel into the past is not merely impractical, but logically impossible, self-contradictory, ruled out by reason itself. But here is the subtle and crucial thing, the thing that Gödel and the physicists who came after him understood, and it changes everything. The paradox only arises if you assume that the traveller arriving in the past can change it, and in a closed time-like curve, that assumption is exactly what fails. The loop is not a sequence in which first the past happens one way, and then later a traveller arrives and alters it. The loop is a single, fixed, self-consistent structure all at once. The traveller arriving in the past was always part of that past. They were there the first time because there is no first time. There is only the one consistent history in which the older traveller is present at the prize, younger traveller's departure, and always was. Think about what this means carefully, because it dissolves the paradox in a way that is stranger and more elegant than simply forbidding time travel. In Gödel's universe, if you travel back to the moment of your departure, then your presence there is simply a fact about that moment, a fact that was always true. When your younger self climbed into the ship, your older self was already there, having arrived from the loop, and your younger self perhaps saw you, and that was always how it happened. You cannot stop. Your younger self from departing, not because some force prevents you, but because your younger self did depart. That is a fixed fact of the one consistent history, and nothing you do can make a fixed fact false. You were always part of the story. Whatever you do, upon arriving in the past, you have already done, and it is already woven into the past you are arriving in. There is no second version of events to change. There is only the one self-consistent loop. This is called the self-consistency principle, and it is the resolution that closed timelike curves demand. They do not allow you to change the past. They allow you to be part of a past that already includes you. The freedom to alter what has happened, which is what generates the paradox, simply does not exist. What exists instead is a single, seamless, self-consistent history in which the loop is already accounted for, in which the traveler from the future was always present in the past, in which everything fits together, without contradiction, precisely because nothing can be changed. The universe permits the loop, but only on the condition that it is consistent, and consistency means the past you visit is the real, fixed, unchangeable past, with your visit already in it. Sit with how this reframes the whole idea of time travel. We usually imagine traveling to the past as an opportunity to do things differently, to change outcomes, to rewrite what happened. That fantasy is precisely what is impossible, and it is impossible not because of any barrier, but because of logic itself. What Gödel's universe allows is something stranger and more humbling. It allows the past to be a place that already contains your future visit. It allows your life to be a closed loop in which cause and effect chase each other around a circle with no beginning. It does not give you power over the past. It reveals the past as fixed, complete, and already inclusive of everything you will ever do within it, including your arrival from the future. The loop is not a do-over, it is a closed ring of events, eternally consistent, in which the question of what came first quietly loses its meaning. Let me push on the self-consistency idea a little harder, because it has consequences that are even stranger than the dissolved paradox, and physicists have thought about them with real care. Imagine a simpler version of a time loop, not a person but a billiard ball. A ball rolls toward the mouth of a time loop, falls in, emerges in the past, and rolls along to strike its own earlier self. Now, you might think you could set this up to be paradoxical by arranging the ball to come back and knock its earlier self away from the loop entrance so that it never fell in to come back. But when physicists worked through such scenarios carefully, they found something remarkable. For every seemingly paradoxical setup, there exists a self-consistent solution, a way the whole thing can happen without contradiction. The ball comes back, yes, but it strikes its earlier self, a glancing blow that nudges it into exactly the path that sends it into the loop at exactly the right angle to come back and deliver that very glancing blow. The loop closes on itself consistently. The apparent paradox is avoided not by forbidding the loop, but by selecting out of all imaginable histories the ones that are self-consistent. Nature, in the presence of a time loop seems to permit only the consistent stories, and it always has at least one available. This is a profound and slightly eerie idea. It suggests that in a universe with closed, time-like curves, there is a kind of global constraint on what can happen, a requirement that the whole history fit together without contradiction, and that this constraint reaches across time, shaping events in the past to be consistent with their own future. It is as if the universe checks the entire loop for consistency before allowing it, and only consistent loops are real. This does not violate any local law of physics. At every point, the ball obeys the ordinary rules of motion, but which of the locally legal histories actually occurs is constrained by the global demand for consistency. The future and the past must agree with each other, because they are joined in a ring, and the ring must close. There is an even deeper puzzle that the loops raise, one that has no tidy resolution, and it is worth naming because it shows how strange these structures truly are. It is sometimes called the bootstrap problem, or the problem of information from nowhere. Imagine that on your journey around the loop, you carry a notebook containing the design for the very rocket you are traveling in. You give the notebook to your younger self before your departure. Your younger self uses the design to build the rocket, makes the journey, and carries the notebook back to give to their younger self. Now ask, where did the design come from? Who invented it? The answer is no one. It was never invented. It exists in a closed loop, copied from the future to the past forever, with no origin, no moment of creation. The information simply is circulating in the ring, uncaused. This is logically consistent. Nothing contradicts, and yet it offends something deep in us, because we believe that information, like everything else, must come from somewhere, must be created, must have a source. The closed time-like curve allows information and causation to exist in a loop with no source at all, a thing that causes itself. That is not a contradiction. It is something perhaps more unsettling than a contradiction, a kind of existence without origin, permitted by the geometry of a rotating universe. Notice what has happened to our ordinary picture of cause and effect. We think of causation as a chain, each event caused by an earlier one, stretching back and back towards some ultimate beginning. The loop replaces the chain with a circle. Around the loop, each event is caused by the one before it, all the way around, and there is no first event, no uncaused starting point, no beginning of the chain, because the chain has no end to begin from. It bites its own tail. This is coherent. The mathematics permits it. But it overturns one of our most basic assumptions, that the web of cause and effect must ultimately rest on some foundation, some origin. In a time loop, the web can curl into a self-supporting ring, holding itself up by its own bootstraps, originating nothing, originating from nothing, simply existing as a consistent whole And here we should pause on what this does to our sense of freedom, because it is part of the vertigo. In a closed time-like curve, you cannot do anything that would make the loop inconsistent. You feel free. At every moment, you seem to choose. And yet, somehow, your choices always turn out to be exactly the ones that keep the loop consistent, that make you arrive in the past in just the way the past always included. It is not that a force stops you from creating a paradox. It is that the only histories that exist at all are the consistent ones, and you are living in one of them, so your choices, whatever they feel like from the inside, are part of a story that was always whole. This is a strange and constrained kind of freedom that can never break the consistency of the world it lives in, because inconsistent worlds simply do not occur. Whether that is freedom at all, or only the feeling of it, is one of the questions the loop leaves us holding, and that is the true vertigo of the closed time-like curve. Deeper than any paradox, it is not that you could change the past. It is that, in such a universe, the very idea of an open, undetermined future flowing into a fixed past breaks down entirely. The loop has no first time and no last time. The traveler causes their own departure, which causes their journey, which causes their arrival, which causes their departure, around and around, a ring of causation with no origin, cause and effect, which we think of as a chain stretching back to some beginning, become instead a circle with no beginning at all. This is what was hidden in Einstein's equations, not a clever trick for visiting yesterday, but a structure in which the deepest features of time, its direction, its openness, the very distinction between what is settled and what is still to come, dissolve into a closed and eternal loop. And the final thing to hold is that none of this is forbidden by the equations. Every step of the loop, every consistency constraint, every uncaused ring of information is permitted by the same general relativity that governs falling apples and orbiting planets and the bending of starlight we have measured countless times. The theory that works, the theory we trust, the theory that runs the satellites in the sky, contains within its family of solutions a world where all of this is real. That is the fact Gödel laid at Einstein's feet. We have walked the loop now, all the way around. Next we must ask what this did to Einstein and what Gödel, in his careful and radical way, believed it truly meant. Now we come to the human heart of the story, and to its deepest idea. Why did this disturb Einstein so much? And what was Gödel, the logician, really trying to say? Because here is the secret that most retellings miss. Gödel did not care, fundamentally, about time travel. Time travel was not his goal. It was his weapon. What he was really after was something far more radical, an argument about the nature of time itself, and he aimed it gently and precisely at his friend. Let us start with Einstein's response, because it tells us a great deal. When Gödel presented his solution, Einstein did not dismiss it. He could not. The mathematics was impeccable, and Einstein knew rigor when he saw it. In his published remarks, responding to Gödel's contribution, Einstein acknowledged that it was an important result, a genuine and significant addition to the theory of general relativity, but he was clearly troubled by it. He admitted that the problem of whether such solutions should be taken seriously had bothered him already in the early days of building the theory, and he raised carefully the possibility that solutions like Gödel's might have to be excluded from physical reality on some grounds not contained in the equations themselves, that perhaps there was a reason beyond the mathematics why nature would not permit such a thing. Notice what a strange and revealing position that is for Einstein to be in. Here was the man who had taught the world to trust his equations, who had insisted again and again that the mathematics of relativity revealed deep truths about reality that defied common sense, that we should follow the equations even when they led to conclusions that felt impossible. He had done exactly that with the bending of time, the curving of space, the equivalence of mass and energy. Follow the math, he had said, even where intuition rebels. And now his friend had followed the math with perfect rigor to a conclusion Einstein himself found difficult to accept, and Einstein found himself reaching for a reason outside the equations to set that conclusion aside. The man who told us to trust the mathematics was now hoping the mathematics could be overruled by something else. That tension, that discomfort, is exactly what Gödel had engineered, because Gödel's real target was not the engineering question of whether one could build a time machine. His target was a philosophical claim about the nature of time, and it was this. Gödel believed that his result showed that the passage of time, the flowing now, the sense that the present moment is special and moving, is not an objective feature of reality. He believed it was, in a deep sense, an illusion. To understand his argument, we have to recall the block universe picture from earlier, the idea that all of space-time, past, present, and future, exists together as a single fixed four-dimensional whole. In that picture, there is already a puzzle about the flow of time. The equations of relativity describe this whole fixed fabric, and nowhere in them is there anything that singles out a particular present moment or that makes time flow. The flowing now, the sense that this instant is real and the past is gone and the future is not, yet does not appear in the physics. It seems to be something we add, something about our experience, not something in the equations. Many physicists had noticed this tension and set it aside, assuming that somehow the objective flow of time was real, even if the equations did not capture it directly. Gödel's argument was a way of forcing the issue, and it went something like this. If the passage of time is objectively real, then there must be an objective, universe-wide sequence of nows, a real flowing present that sweeps through all of reality, the same for everyone, dividing the settled past from the open future. But in his rotating universe, no such universe-wide flowing present can be defined, because the time loops, because The cones tilt around and the past connects to the future. There is no way to slice the whole universe into a consistent stack of moments. No way to define a single objective, sequence of nows that everyone could agree on. No coherent universal present marching forward. The very structure of the space-time forbids it. And here is his crucial move. If, in this universe, the objective passage of time cannot exist, then the passage of time is not a necessary feature of reality. It is not built into the nature of things. And Gödel argued that if it is not necessary, if there are valid universes where it simply cannot exist, then it is probably not truly objective even in our universe either. The flow of time, he suggested, is a feature of our experience, of how we are embedded in the world, not a feature of reality itself. Time, in the deepest sense, does not pass. We only experience it as passing. There is a phrase that captures the move, and it is worth saying slowly. Gödel argued that if the lapse of time cannot exist in some possible worlds, then it does not truly exist in any world, including ours, because something that is genuinely real should not depend so delicately on the contingent arrangement of matter. A real feature of the universe, he felt, should be robust, should not vanish merely because the cosmos happens to rotate. And since the flow of time does vanish in his rotating world, he concluded it was never a fundamental feature to begin with, only an appearance, a product of how creatures like us are stitched into the fabric. This is a breathtaking claim, and it is what Gödel was really reaching for all along. The time travel, the rotating universe, the closed loops, all of it was in service of this one philosophical strike. He was using physics to argue that our most intimate, most certain experience, the flow of time, the movement of the present, the goneness of the past is not a truth about the world, but a feature of our limited perspective within it. The past is not gone. The future is not open. They simply are all at once in the fixed fabric of space-time, and our sense that we are moving through them, that now is special and flowing, is something like an illusion generated by how a conscious being experiences its own world line. We feel time flow the way we might feel motion on a train, a real experience that does not correspond to any absolute flowing of the world outside. It helps to make concrete what it means that there is no universal now, because this is the piece of relativity that already softened the ground for Gödel's argument. Imagine two events far apart in space, say a flash of light on a distant world and a flash here on Earth. Ask whether they happen at the same time. In the old physics, this question always has a definite answer, because there is one universal clock. But relativity showed that the answer depends on how you are moving. To one observer, the two flashes are simultaneous. To another, moving differently, the first happens before the second. To a third, the second happens before the first. And none of them is wrong. There is no fact of the matter about which event is really first, because simultaneity is relative. This means there is no single, universe-wide present moment that everyone shares. Your now and my now, if we are moving differently, slice the fabric of space-time at different angles, and neither slice is the true one. The present, that thing which feels so absolute and so universal, turns out to be a personal and perspectival thing, different for differently moving observers. Now, feel the pressure this already puts on the idea of a flowing time. If there is no universal present, then what exactly is doing the flowing? The flow of time, as we imagine it, is the movement of a single present moment from past toward future, the same for all of reality. But relativity says there is no single present to move. Each observer has their own slicing, and the slicings disagree. So the comfortable picture of one universal now sweeping forward through reality is already in deep trouble before Gödel ever arrives. Many physicists noticed this and tried not to think about it too hard, holding on to the feeling that time really flows even though the physics seem to dissolve the universal present that flowing would require. Gödel walked straight into that uncomfortable gap and widened it into a chasm. His rotating universe does not merely make the present relative. It makes any consistent global ordering of moments impossible, because the loops tangle past and future together so thoroughly that you cannot even stack the moments into a sequence. Relativity had taken away the universal now. Gödel took away the very possibility of a coherent cosmic sequence of nows at all, and you can see why this would disturb Einstein especially, because in a strange way it completed something Einstein himself had started and then flinched from. Einstein had already dismantled the absolute present of older physics. He had shown that simultaneity is relative, that there is no universal now shared by all observers, that whether two distant events happen at the same time depends on your motion. He had gone a long way toward removing the objective present from physics, but he had not fully embraced the conclusion that the flow of time is unreal. Many believe Einstein did, in his heart, lean toward the view that the distinction between past, present, and future is a kind of stubborn illusion. There is a famous remark attributed to him near the end of his life, consoling the family of a friend who had died, suggesting that the distinction between past, present, and future is only a persistent illusion. So Einstein was perhaps already half persuaded, and Gödel, his friend, handed him a rigorous mathematical argument that pushed all the way to that conclusion, using Einstein's own theory to do it. It was an intimate philosophical gift and an intimate philosophical challenge from one deep mind to another. Whether Gödel's argument fully succeeds is still debated by philosophers, and we should be honest about that. Many thinkers have pushed back. They point out that even if some possible universes cannot have an objective flow of time, it does not strictly follow that our universe lacks one. Perhaps the flow of time is real in universes that have the right structure to support it, and merely absent in strange ones like Gödel's. The logical leap from possible to actual From could not exist there to does not exist, here is the contested step. But the power of the argument is not in whether it is airtight. The power is in how it forces the question into the open. Gödel made it impossible to comfortably assume that the flow of time is obviously real, by showing that the very theory we trust most permits worlds where it cannot be. He turned a vague philosophical worry into a sharp mathematical fact, and that fact still sits there, unresolved, at the foundation of how we think about time. Let me dwell on the relationship between these two men a little more, because the philosophy and the friendship are not separate things here. They were intertwined. Gödel did not aim this argument at a stranger or a rival. He aimed it at the person he walked with nearly every day, the person whose theory he admired enough to spend years mastering, the person who, by some accounts, was the closest thing Gödel had to a true intellectual companion in those Princeton years. There is something tender in that, and something fierce. To take your friend's greatest creation, master it completely, and then use it to challenge his deepest assumptions about reality is an act of profound intellectual intimacy. It is the kind of gift only one great mind can give another, a gift that says, "I have understood your work so well that I can show you something in it you did not see, something that troubles even you." It is love expressed as rigor, and the two of them were, in temperament, almost opposites, which makes the meeting of minds more remarkable. Einstein was intuitive, physical, guided by a feel for how nature ought to behave, by a sense of beauty and simplicity. Gödel was austere, logical, guided by proof and by a relentless refusal to assume anything not strictly demonstrated. Einstein trusted his physical intuition and used mathematics to express. Gödel trusted only the logic and followed it wherever it led, even into places that felt impossible. And yet on the question of time, they converged. Both, in the end, seemed to have leaned toward the radical view that the flow of time is not a fundamental feature of reality, that the universe is in some sense a complete and timeless whole, and that our experience of passage is a kind of perspective effect. Einstein arrived there by intuition and a lifetime of dismantling absolute time. Gödel arrived there by constructing a rigorous proof. Different roads, the same strange destination. It is worth understanding why this view of time appealed to Gödel so deeply, because it connects to who he was as a thinker. Gödel was, in his philosophy of mathematics, a Platonist. He believed that mathematical objects and truths exist objectively, timelessly, independent of human minds, in a realm that does not change and does not flow. Numbers do not come into being and pass away. Mathematical truths are not invented, but discovered, eternal, already there. For a mind that saw the deepest reality as timeless and unchanging, the idea that physical time also might not truly flow, that the universe might be a fixed, eternal structure like the realm of mathematics, would have felt natural, even beautiful. Gödel was not disturbed by the timeless block universe the way many are. He was, if anything, drawn to it. It fit his sense that the truest things are the ones that do not change. His rotating universe was, in a way, an attempt to show that physics itself points toward the timeless reality he already believed in. Now let us be fair to the other side, because the question is genuinely open. Honesty demands it. Not everyone accepts Gödel's conclusion, and the objections are serious. The central worry is the leap from possibility to actuality. Gödel showed that there exist valid universes in which an objective flow of time cannot be defined. From this, he concluded that the flow of time is not an objective feature of reality in general, and therefore probably not in our universe either. But a critic can reasonably say, why should the strange properties of a universe we do not live in tell us anything about ours? Perhaps the flow of time is perfectly real here, supported by the actual structure of our cosmos, which is not Gödel's rotating one. Perhaps time flows in universes built to let it flow, and fails to flow only in exotic constructions like Gödel's, and ours is the former kind. The mere existence of a possible world without flowing time does not obviously prove that our world lacks it. This is a real and respectable objection, and the debate continues among philosophers to this day. Gödel's argument is not a proof that closes the question. It is a provocation that opens it and keeps it open. But even granting the objection, something of Gödel's challenge survives, and it is this. He showed that the reality of time's passage cannot simply be assumed, cannot be taken as an obvious given, because the very physics we trust most permits worlds where it does not hold. He moved the flow of time from the category of unquestioned background fact into the category of things that must be argued for, defended, established. Before Gödel, one could comfortably assume that of course time flows, that this is just how reality is. After Gödel, that comfort is gone, because he showed with mathematical precision that the flow of time is not guaranteed by the laws of physics, that it is at best a contingent feature of certain universes and not a necessary feature of all of them. That shift from assumed to questioned is itself a permanent achievement, regardless of where the debate finally lands. So this was the true nature of the birthday gift. Not a toy, not a paradox for its own sake, but a profound and carefully aimed argument that time itself, the most intimate feature of our existence, may not be what it seems, may not flow at all, may be a still and complete fabric that we merely experience as passing. Gödel gave Einstein, on his 70th birthday, a reason to doubt the reality of time, and Einstein, who had spent his life remaking our understanding of time, received it, took it seriously, and could not quite refute it. What remained was the question Einstein raised in return, the question of whether reality, our actual universe, somehow forbids these structures even though the equations allow them. That is the question we turn to last. The gap between what the mathematics permits and what the cosmos appears to build. Let us go there now and see why our universe seems to say no. So we arrive at the final question, the one Einstein raised in return, the one that has hung over this whole story from the beginning. The mathematics permits a universe with time loops. But do we live in such a universe? Is the past actually reachable in our cosmos? Or is Gödel's universe a beautiful possibility that nature, for whatever reason, simply did not build? And the answer, as best we can tell, is that our universe does not allow it. The loops are real in the mathematics and absent from reality. Let us understand why. Gödel's universe has two defining features, and our universe matches neither of them. The first is that Gödel's universe rotates. The second, just as important, is that Gödel's universe does not expand. It is static, unchanging in its overall size, holding its rotating configuration steady forever. Our universe is the opposite on both counts. Our universe, as far as every observation can tell, does not rotate, and it most certainly does expand. And those two differences are enough to close the door that Gödel opened. Start with the expansion. One of the great discoveries of 20th century astronomy is that our universe is expanding, that the galaxies are flying apart, that space itself is growing. This was found by observing that distant galaxies are receding from us. Their light stretched toward the red by the expansion, and the further away they are, the faster they recede. Run that expansion backward in time and you reach the hot, dense beginning we call the Big Bang. Our universe has a history, a direction, a growth from a dense past toward a thinner future. And this expansion gives our universe something Gödel's lacks. It gives it a natural cosmic time. Because the universe is expanding in an orderly way, you can use the expansion itself as a universe-wide clock. How dense the universe is, how stretched the ancient light is, how far the galaxies have flown, all of these increase steadily with cosmic time, giving every observer a shared way to say how far along the history of the cosmos they are. This cosmic time provides exactly the kind of consistent global ordering of moments that Gödel's rotating universe forbids. In our expanding universe, you can slice the whole of space-time into a clean stack of moments labeled by cosmic time, never tangling, never looping. The expansion combs the moments into order. Now the rotation. Does our universe rotate as Gödel's does? This is something we can actually test, and people have looked carefully. If the universe as a whole were rotating, it would leave subtle fingerprints in the way distant galaxies are oriented, in the patterns of the ancient light left over from the Big Bang, in slight preferred directions woven into the large-scale structure of the cosmos. Astronomers have searched for these signatures, and they have not found them. Every measurement is consistent with a universe that does not rotate at all, or that rotates so extraordinarily slowly that the effect is undetectable and far too small to permit any time loops. Our universe, as best we can measure, has no global spin, and without the rotation, the central mechanism of Gödel's construction, the swirl that tilts the light cones around into a ring, is simply absent. The cones in our universe stay upright, neatly ordered, pointing into a shared future, the guardrails of causality firmly in place. There is a poignant detail here that I love, and it tells you something about Gödel's seriousness. He did not treat his rotating universe as a mere abstraction to be admired. He wanted to know whether it was real. And so Gödel, the logician, went and looked at the data. He studied the astronomical observations of his day, the measurements of galaxy orientations and motions, searching for evidence that our actual universe might be rotating. He took the question seriously enough to do the empirical work, to ask reality directly whether it had the spin his universe required, and he found no clear evidence of cosmic rotation. The universe, as far as he could tell from the data, did not turn. He had built a world where time loops, and then honestly checked whether it was our world, and the answer that came back was, apparently not. There is something deeply admirable in that. The willingness to subject his own beautiful construction to the test of observation and to accept what the observation said. So the consensus among physicists is that our universe does not contain closed, timelike curves of the Gödel kind, because we do not have the rotation and we do have the expansion, and together those features keep time orderly and the past sealed. The loops live in the mathematics, in a possible world, but not in ours. And later physicists went further, proposing that perhaps there is some deep principle of nature that actively prevents time loops from forming under realistic conditions, a kind of protection of causality built into the laws, ensuring that whenever you try to create the conditions for a time loop, something always intervenes to prevent it. This idea that nature defends the consistency of history against the formation of loops remains a conjecture, not a proven theorem. But it captures a widespread intuition among physicists that the universe somehow does not permit the past to be rewritten or revisited, that causality is protected. But here is where we must be careful, and where the real meaning of Gödel's discovery lies, because it is easy to feel relieved at this point and conclude that the loops were ruled out and the problem is solved. That conclusion misses the entire point. The loops were not shown to be impossible. They were shown to be absent from our particular universe. The mathematics still permits them. General relativity, the theory we trust, the theory that has passed every test, still contains within its family of solutions a world where the past is reachable. We do not live in that world, as far as we can tell, but the theory allows it. And that gap between what the theory permits and what reality appears to contain is one of the most profound and unsettling things in all of physics, and it does not go away just because our universe happens to be on the safe side of it. Think about what that gap means. We tend to assume that our best physical theories describe reality, full stop. That if the equations say something is possible, then it tells us something about how the world can be. But Gödel's universe is a valid solution to our best theory of gravity that, as far as we can tell, does not correspond to anything real. The theory is, in this sense, more permissive than reality. It allows more than nature builds. And that raises a deep question about the relationship between mathematics and the physical world. Why should the equations permit universes that do not exist? Is Gödel's universe simply a mathematical phantom, allowed by the formalism but excluded by some deeper principle we have not yet identified? Or is it a genuine possibility, a way a universe really could be, that simply did not happen to be actualized in our case? We do not know. The equations do not tell us why nature chose the solutions it did and not the others. They only tell us which are allowed. And so Gödel's gift, in the end, was not really about time travel at all, just as he intended. It was about the limits of our knowledge and the strangeness of time and the gap between the possible and the actual. He showed that our deepest theory of space and time contains, hidden within it, a world where the past is not gone, where time closes into a loop, where the flow we feel so certain of cannot even be defined. He could not make our universe into that world, and the data suggest our universe is not that world. But he showed that the world we trust the equations to describe is, at its foundations, far stranger and more open than we had let ourselves believe. The past being gone, the future being open, time flowing forward. These are not theorems of physics. They are features of our particular cosmos, perhaps, or features of our experience, but not necessities written into the nature of things. And once you have seen that, you cannot unsee it. It is worth knowing that Gödel's universe was not the end of the story of time loops in physics, but the beginning of it. He was the first to find a clean, exact solution to Einstein's equations containing closed timelike curves, and in doing so he opened a whole field of inquiry that continues to this day. After Gödel, physicists found other solutions, other ways the equations seem to permit paths into the past. Some involve impossibly long, dense, rotating cylinders whose spin drags space-time around enough to tilt the cones into loops near them. Some involve the interiors of certain rotating black holes whose strange inner geometry appears on paper to contain closed time-like curves, and later physicists studying wormholes, hypothetical tunnels through space-time, realized that if such tunnels could be made and manipulated in certain ways, they too could in principle be turned into time machines. Each of these is, like Gödel's universe, a valid or near-valid solution to the equations, and each, like Gödel's universe, seems to be hedged about by reasons to think nature would not actually permit it. Exotic matter that may not exist, instabilities that would tear the structure apart, conditions that cannot realistically be met. The pattern that Gödel established has held. The equations keep offering doors to the past, and reality keeps appearing to slam them shut, but never with a final, decisive proof that they are shut forever. This is why some physicists have proposed that there must be a deep principle, not yet fully understood, that protects the consistency of history, that prevents time loops from actually forming no matter how cleverly you try to arrange matter to make one. The idea is that whenever you push the laws toward creating a closed time-like curve, something always rises up to stop you, some build-up of energy, some instability, some quantum effect that destroys the structure before the loop can close. On this view, nature is not merely accidentally free of time loops. It actively defends against them. It protects the past. This remains a conjecture, unproven, but it expresses a widespread feeling among physicists that the universe simply will not allow the kind of paradoxical structure that revisiting the past seems to threaten. And yet, and this is the crucial point, even if such a principle exists, it would be an additional principle, something beyond general relativity, something we would have to add to the theory to forbid what the theory by itself permits. The bare equations of general relativity still allow the loops to rule them out. You have to bring in something more. Gödel showed that relativity alone is not enough to protect causality. That, by itself, is a permanent and humbling result. Let me draw out the deepest lesson, the one that makes this more than a historical curiosity. We build mathematical theories to describe the world, and when they succeed, when they pass test after test, we begin to feel that they capture reality, that the world simply is what the equations say. Gödel's universe is a standing reminder that the relationship is subtler than that. A successful theory can permit more than reality contains. The equations of general relativity describe our universe beautifully, and they also describe Gödel's universe, and Venus would be no stranger to us than Gödel's world is, except that Gödel's world appears not to exist. So the equations are, in a sense, a map of all the universes that could be, and our universe is just one point on that map, one solution among infinitely many. The other solutions are not errors. They are not mistakes in the theory. They are genuine possibilities the theory allows. Roads not taken, universes not built, and we do not fully understand why reality took the road it did. Why our universe is the expanding, non-rotating one, rather than the spinning Gödel one. Why the past is sealed here when the equations would let it be open. The theory does not explain its own actualization. It lays out the possibilities and falls silent on the choice. There is a humility in that worth carrying with you. Our deepest physics does not hand us a single necessary universe. It hands us a vast space of possible universes and leaves us to discover, by looking, which one we happen to inhabit. And sometimes, as with Gödel's universe, it shows us a possibility so strange that we are relieved to find we do not live in it, and yet so rigorously permitted that we cannot quite dismiss it, and we are left holding the unsettling knowledge that the laws we trust would have allowed our most basic assumptions about time to be false. The past being gone is not a law. It is, here, a fact, a feature of our cosmos, and the equations would have let it be otherwise. And there is, I think, a quieter and more personal thing to take from all of this beyond the physics and the philosophy. Gödel's deepest claim, the one he aimed at Einstein, was that the past is not gone, that in the true structure of reality, the fixed four-dimensional fabric, every moment that has ever happened is still there, as real as this. One, not erased, not fallen into nothingness, but held permanently in the geometry of spacetime. We experience time as a flowing that leaves the past behind, a relentless current that carries everything we love away into a vanished yesterday. But if Gödel and perhaps Einstein were right, that flowing is something about us, about how a conscious being moves along its own world line, and not about reality itself. In reality, nothing is lost. Every moment you have lived still exists, fixed in the fabric, complete. The afternoon you are half remembering, the people who are gone, the version of yourself from years ago, none of them have been annihilated. They are simply elsewhere in space-time, as real as a distant city you cannot currently visit, but that exists nonetheless. Whether that thought is a consolation or a vertigo depends on how you hold it, and people have felt it both ways. There is something almost unbearable in the idea that the present has no special status, that the now you are living is not more real than any other moment, that the flow you feel so vividly is in some sense a trick of perspective. And there is something tender in it too, in the idea that nothing truly passes away, that the past is not destroyed but preserved, that everything that has ever been still is. Einstein, consoling a grieving family near the end of his own life, seemed to find comfort in exactly this, in the thought that the distinction between past, present and future is a stubborn illusion, and that those who have gone before have not vanished but merely occupy another region of a reality that does not erase its own moments. Gödel gave that intuition a rigorous spine. He showed that the physics we trust does not require time to flow, does not require the past to be gone, and contains within it worlds where the past is as reachable as any other place. He could not prove that ours is such a world, but he proved that the goneness of the past is not a law of nature. It is, at most, a feature of where we happen to live, and at least a feature of how we happen to experience the one fixed fabric that holds us. So let us return at the last to where we began, to Princeton, to two friends walking slowly home together in the late afternoon, the most famous physicist in the world and the greatest logician of the age, talking quietly in German about the structure of reality. One of them has just given the other a universe for his birthday, a universe in which you can travel into your own past, pulled rigorously from the other's own equations. They both know it is probably not our universe, and they both know that this hardly matters, because the point was never our universe. The point was what the equations permit, what reality might have been, what time truly is beneath the flow we feel. Einstein will raise his careful objection that perhaps such worlds are excluded on physical grounds. Gödel will hold, quietly, that the very possibility tells us something true about time. Neither will fully convince the other. The question will outlive them both, and it is still here, unanswered in the equations, waiting the way Gödel found it, the way it will remain. The past in his universe was never gone, and the question he handed his friend on a spring afternoon in 1949 has never gone either. It is still with us, still open, still turning, like a universe that quietly spins